Before we begin our discussion on reaction quotients, let's look at one last equilibrium constant example. This example involves looking at heterogeneous equilibria. What we mean by that is that the reactants or products are in different phases. So here we have two solids and a gas. If you recall, whenever we're writing an equilibrium constant, we do not include solids or liquids. So the equilibrium constant with respect to concentration would just be equal to the concentration of CO2 here. If we were looking at the equilibrium constant with respect to pressure, it would just be the partial pressure of CO2. And if there was a coefficient in front, then we would also put that in the exponent in our equilibrium expression. Alright, so now we're going to start to use the equilibrium constant to figure out how far a reaction is going, or in which direction it's going. So here, let's go ahead and look at this example for the formation of water. So we have H2 plus O2 yields 2H2O. So if we write our equilibrium expression out, we'll get Kc is equal to the concentration of H2O squared over the concentration of H2 squared times the concentration of O2. Now whenever we look at the value of Kc, we see this is a huge number, 2.4 times 10 to the 47th. So whenever we look at that Kc value, since this value is much greater than 1, this means that this reaction is essentially all products. So what we could do is we could go through and figure out for a given concentration of H2O what the concentration of H2 and O2 are. What we'll see is there's very little concentration of the H2 and O2 molecules. If we look at the reverse reaction, so in this case H2O dissociating to form H2 and O2, if we write out that equilibrium constant expression, we'd have Kc is equal to H2 squared times O2 all over H2O squared. What we'll see here is this Kc value is 4.2 times 10 to the negative 48th. So what that means is the reactants are dominating this reaction. So there's not a whole lot of products. So only the reactants would really be favored. There would not be an appreciable concentration of either of the products in this case. But we can use Kc to determine whether a reaction is favored more going forward in the forward direction or in the reverse direction. So what we'll say is if Kc is greater than something to the order of 10 to the third, then the reaction will proceed nearly to completion. So if we have our generic example, A plus B goes on to form D plus E. In this case, if Kc is greater than 10 to the third, this is essentially all products whenever we've reached equilibrium. There's very little of the reactants remaining. However, if Kc is 10 to the negative third or smaller, that means the reaction doesn't really go forward at all, and we're more or less stuck with the reactants. But then most of the time what we'll see is, in examples, is that Kc is somewhere in the range of 10 to the negative third to 10 to the positive third. What that means is there's an appreciable concentration of both the reactants and products present. So the next thing that we want to do is we want to actually be able to predict the direction that a reaction will go from a given point in time. So far, whenever we've been looking at a Kc value, so the equilibrium constant, we're always given concentrations whenever the reaction is at equilibrium. Well, now we're going to look at concentrations whenever it's just measured at some time t. So we don't know whether it's at equilibrium or not. But whenever we write this relationship between the concentrations, we call this a reaction quotient. And so this would be Q sub C. Okay, and whenever we write a reaction quotient, we write it in the exact same way that we would a Kc value. So here, if we look at our reaction up here, we have H2 plus I2 yields 2HI. So here, the reaction quotient would be HI squared over H2 times I2. So that's our reaction quotient. And if this was at equilibrium, Kc would be 57. But we don't know yet if it's at equilibrium or not. So what we're going to do is we're going to plug in our concentrations at some time t. So we'll have QC is equal to the concentration of HI, which is 0.40. We'll square that, divided by the concentration of H2 times the concentration of I2. Whenever we plug that in, we should get that the QC value is 8. So what we'll see is that QC is 8 and KC is 57. So since QC does not equal KC, that means that we are not at equilibrium. So from here, we can try to predict which direction the reaction will go. So if we need to make this value larger, that means we need more products. So that means since QC is less than KC, the reaction is going to proceed to the right. We're going to form more products. So if we look here, we can compare QC to KC in any case. So if QC is less than KC, the reaction goes from left to right, so it goes towards the products. If QC is too big, so if it's greater than KC, then it goes back to the left to form more of the reactants. And if QC is equal to KC, then no net reaction occurs, and then we're said to have a dynamic equilibrium. Let's go ahead and do a few examples. So we have a mixture of 1.57 moles of N2, 1.92 moles of H2, and 8.13 moles of NH3. And this mixture is introduced into a 20-liter reaction vessel at 500 K. So what we know is that the equilibrium constant at this temperature is 1.7 times 10 to the second. So we need to find out whether this reaction is at equilibrium or not. So the first thing we want to do is we want to convert these mole amounts into concentration. So we'll take, for instance, for nitrogen, we'll take that 1.57 moles divided by the volume of our container, which is 20 liters, and we will get a concentration 0.0785 molar. And we'll repeat this process for all the reactants and products. We'll find the concentration of H2, 0.0960. I'd recommend checking these concentrations in case I made a silly mistake. The concentration of ammonia is 0.407 molar. So now what we're going to do is we're going to write out our expression for QC. We don't know if this is at equilibrium or not, so we're finding the reaction quotient, not the equilibrium constant. So we have NH3 squared over N2 times H2 cubed. So now what we can do is we can go ahead and plug in our concentrations. So we'll have 0.407, that will be squared, divided by the concentration of N2, 0.0785. Remember, just like KC, QC does not have any units. Okay, so we plug all that in, and whenever we solve this out, we get 2.39 times 10 to the third. And again, make sure that you're being careful and following your orders of operations for the denominator so you don't make a silly math error. So, the question we ask, whenever we find a reaction quotient, does QC equal KC? Well, whenever we look at our data here, we have a QC of 2.39 times 10 to the third, a KC of 1.7 times 10 to the second. So no, they are not equal. And in this case, QC is greater than KC. So that means the reaction will proceed to the left. Here's another example. And here we're given Kc for this reaction. Nitrogen monoxide plus oxygen going on to form nitrogen dioxide. We know the equilibrium constant is 6.9 times 10 to the fifth. We have a 5-liter reaction vessel, so you'll have to go through and convert all your molar amounts or your moles into concentrations, so you'll have to divide all of those by your 5 liters. But then you'll go ahead and plug in to your reaction quotient. So here we'll go ahead and write the expression again. So we'll have QC is equal to the concentration of NO2 squared over the concentration of NO squared times the concentration of O2. So whenever we plug in our values, so we have 0.16 squared over 0.012 squared times 0.20, we find that QC is 8.9 times 10 to the second. Well, this number is 3 orders of magnitude smaller than Kc, so that means the reaction is going to proceed to the right for this set of conditions. So go ahead on your own, calculate what QC should be for this set of conditions, these initial amounts, and predict whether or not the reaction goes to the left or to the right. All right, we have one more thing to cover before we get into ice charts. So here, in this example, we're looking for what is the concentration of NO in an equilibrium mixture of gaseous NO, O2, and NO2 at 500 K. So we know the concentrations of O2 and NO2, and we know what Kc is. So let's go ahead and start by writing out our equilibrium expression. So we'll write Kc is equal to NO2 squared divided by NO squared times the concentration of O2. All right, well, in this case, notice that we know the concentration of O2, we know the concentration of NO2, and we know what Kc is. So that means we're going to solve for the concentration of NO. So what we're going to do is we're going to cross multiply and divide. So we'll get NO, that concentration is equal to NO2 squared divided by Kc times the concentration of O2. This whole side we'll take the square root of. Alright, so what we're going to do is we're going to plug in our concentrations. We're going to plug in Kc. We're going to take the square root of that side. So now this is where sometimes people will forget a step. So we know that Kc doesn't have any units. But whenever you use Kc to solve for a concentration, you have to remember to put the units back on. So whenever you plug in, you should end up getting that the concentration of NO at this equilibrium concentration is 1.9 times 10 to the negative third molar. And again, here we used Kc instead of QC because in the problem it tells us that it was an equilibrium mixture. So that means we are at equilibrium. So we use a K value, not a Q value. All right, so that will go ahead and finish our lecture on reaction quotients. Next time we'll pick up with ice charts.